So in the fourth lecture, we covered the rotation representations, and now we will today in this lecture um, talk about the actual robotics topic of solving, first of all, representing the configuration of a robot, of a manipulator, and that will lead to the solution of direct position kinematics. And by solving the resulting equations, we will actually solve the inverse position kinematics problem. Okay. So we first covered the 2D rotation, combined it with translation, getting 2D rigid body motion together, and then we did the same thing for 3D. In between, we took a break and discussed the different 3D rotation representations. This one, and on the way, we discussed the composition rules of successive rotations and therefore successive rigid body transformations and their inverses also. Fine. Next, we discussed how the same 4x4 homogeneous transformation matrix can represent a rigid body motion as well as position and orientation. In brief, termed as or referred to as pose. Okay. And now, in a robot manipulator, every link is assigned a frame of reference. Right? Now, through joints, typically revolute joints and prismatic joints, though in more complicated kinds of manipulators, there are spherical joints also, and other kinds of joints possible. Okay. But mostly it is revolute joints and prismatic joints. In serial chain manipulators, with which most of this course will deal, it is mostly open chain, so revolute and prismatic. In an open chain mechanism, open chain linkage, open chain manipulator, there is no way to have a spherical joint because spherical joint actuation is not in the technology. Okay. Now, to one link, you attach another link, to that, you attach another link, and like that, from the frame which is fixed to the hand and effector, the sequence of links proceed. That is typically. If an atypical situation arises where there are branch chains, then the same formalism has to be applied again for the branch chain separately from the point of departure. Anyway, so frame is the link 0, then link 1, then link 2, and so on. So in this sequence, suppose there is a link here, link I minus 2. Okay? And then with that, at this axis, at this joint, you have attached link I minus 1, to which at this joint, you have attached link I. And so you have link 0, which is frame. After that, axis 1, link 1. Axis 2, link 2. So you do not have any axis 0. So link I minus 2, then axis I minus 1, and so on. Now think of one thing. When you have this axis I minus 1 and the next axis I, then what can be the most general relative disposition between the two axes? So look at these fingers. Look at my fingers. Like this. Okay. So they need not be parallel and they need not be coplanar. So these lines are skew. Okay. So which have a distance between them. That is a minimum distance and that is a normal distance. Okay. So that normal distance and that direction of the common perpendicular plays an important role in the way we assign the frames of reference. So with link I minus 1, the frame of reference has to be positioned, that is the origin of the frame of reference has to be at the common perpendicular between this axis I minus 1 and the next axis I. And this is a convention, and this convention was proposed in 1955 in a context which was not exactly robot kinematics, but robot kinematics has adopted it. So this was proposed by Denavit and Hardenberg, and this is a very uh, universally applicable convention, so everybody has accepted it. So at the common perpendicular, you put the origin of the link frame I minus 1, which is the frame of this link. That is, it is attached to this link. Now, for every frame, you work out the z-axis along the axis of relative motion. If it is revolute here, revolute joint, then it is the axis of rotation, and if it is prismatic joint, then it is the direction of or the line of relative sliding. Okay. So along that you put the z-axis, and x-axis of that is put along the common perpendicular from this foot of the perpendicular to that foot of the perpendicular. Okay. So this is the x-axis, and this is the z-axis, and therefore the y-axis gets settled. Z plus x unit vector along z direction plus unit vector along x direction will give the unit vector along y direction. Fine. So you have got the frame of reference here. And then consider here. Here for the link I, the frame of reference I that you will have to put, that will have its z axis along this axis. You would be tempted to suggest that put its origin here, but that you can't do, because this fellow's origin you will have to put at the foot of the perpendicular, foot of the common perpendicular between axis I and the next axis, which is axis I plus 1. Okay, so it may be somewhere here, not necessarily here. In general, it will not be here. Okay, so now 4 quantities will arise that will describe completely the relationship between this frame of reference and this frame of reference. Relationship, or you say that by how many fundamental motions, only rotation or only translation, you can move this frame from here to here. And that will actually describe the position and orientation of the next frame, that is the next link, with respect to this one. So what you need to do? So for that, this z-axis and this z-axis, between the two z-axes, you can work out the angle. For that, draw parallel to this z-axis, a line through this, and then whatever that line makes an angle with this. that is one parameter alpha. Okay. We call it alpha I minus 1. Next one will be alpha I and so on. So you start the whole thing with alpha 0. Okay. And this is called twist angle. Why twist angle? Because if the axes were parallel, I'll make it a little smaller so that it is visible better. Yeah. So this is called twist angle because if the links were such that two axes were parallel, then you see you would not need this. It will be straight and parallel. Now, whether through a curve or by two, I mean, an angular kind of link shape to achieve this uh, inclination between the two axes, it's up to you. Whatever way you do it, it's a twist. Okay, so that is a twist angle. If the twist angle is 0, then the two axes are parallel. Okay, link goes straight. Then, if the link were straight, that is, if the two were parallel, then you see the distance between the two axes would be all through. There will be then parallel. Okay, so all through that will be constant. Okay, and that would be the link length. That would be the length of this link from here to here. So even if it is twisted, this quantity, the length of the common perpendicular, is called the link length, and that is denoted as a I minus 1. So we start the game with a 0. Fine. And now, after that, we have come here in a way. So you see now, if you turn this frame of reference through the x-axis, to the local x-axis by this angle, then what happens? This angle between zi minus 1 and zi. Now, if you turn it about, and the common perpendicular is this. So, if you turn this frame of reference, x, y, z, xi minus 1, yi minus 1, zi minus 1, about this x direction, then what happens? Y and yz plane turns, and if your rotation is this much, then zi minus 1 turns and becomes parallel to z. After that, so it will be basically going like this, okay? Going like this, parallel to this. Then, if you move the frame along this x direction, see the rotation was about the x-axis. Now the translation is also along the x-axis. If you translate it here, then what happens? X remains here. Z, from being parallel to Zi, now becomes coincident. Okay. Of course, the origin is elsewhere, and this fellow's x is this way. This fellow's x is this way, and this fellow's x is this way. Perhaps decided based on how the next link is. So that angle between this direction xi and this direction xi minus 1 is called the joint angle, because that will change if you turn this link at this joint about this axis, then it will change. So that is the joint angle. That is a variable typically. Typically, I say, keep note. Okay. So then you can do two more things. One, rotate this frame about zi axis. Okay. Now that is the same as zi minus 1. So local through angle theta I. Now you see theta I, joint angle. So whatever parameters, whatever coordinates we are talking about at this end, that is given the index I. So here it was I minus 1. Okay. So theta I. So then what will happen? That was coincident. Now also it is coincident. X and Y axis of this frame become parallel to X and Y of this frame, and then this length, if you traverse along the same axis, Z axis, through this distance di, which is called the frame offset. Why the frame offset? Because the common perpendicular was here, and the next frame could not be put there; it was put here. So this is the frame offset. Okay. By that, if you move it along this, then now after this fourth unit of motion, fourth change in this frame has become completely coincident with this frame. And that means if you compose these four component motions together, one after the other, post multiplication, because each of the change we have made in the local frame, then you would be representing this fellow's position and orientation in this plane of reference. Okay? So now, out of these four parameters, these four variables, these four quantities are called alpha, twist angle, A, link length. These are referred to the previous index, I minus 1. These are design parameters. Both of them are fixed by design. Then you have here D, which is the frame offset, and theta, joint angle. These are referred to the next index, I. These are typically, one of them is a design parameter, fixed, and the other is the joint variable, which you change by the actuator during the operation of the manipulator. So, if the joint is revolute, this joint I. If this joint I is revolute, then frame offset B is fixed. This is the joint variable. On the other hand, if it is a prismatic joint, sliding joint, then this theta is rigid. That is how it is made, design parameter, and the di is the variable. Now compose these four motions. Now make note that in 3D motion, rotation, translation, commutativity does not exist in general. But if the rotation is about an axis and the translation is also along the same axis, then whichever way you give those motions, whether you first translate and then rotate or do the other way around, it doesn't matter. The final configuration turns out to be the same. And therefore, the same thing happens in the matrix multiplications also. So, in such circumstance, matrix multiplication is commutative. So, whether these two motions, rotation about x-axis through this twist angle and translation along x-axis, same x-axis, through this link length, you give in this order or that order, it doesn't matter. Similarly, here also, both the motions, the translation along the z-axis through the frame offset and rotation about the z-axis only through the joint angle, whichever way you give, whichever order you give, it doesn't matter. But the order of these two and those two will matter. So anyway, so you say rotation about x, I minus 1 by alpha I minus 1. That is this. This is the rotation. And translation. So if you write only this as one matrix, then this part will be as it is. T means cosine, S means sine. And this part would be 0, 0, 0, 1. In the case of translation only, if you write, then this part will be identity. This 3 by 3 part will be identity. And this will be AI minus 1, 0, 0, 1. I have already multiplied them. And that multiplication will be same. That product will be same whether you do it in this order or the other order. Similarly, these two, translation along Z and rotation about Z, whichever order you do it, it will turn out to be the same. And I have written the product to basically condense one step in between. So this is the rotation part of it. and totally decoupled the translation part of it. Okay, you can multiply these two and get whatever complicated full expression of the 4x4 transformation matrix that you get, and that will be fine. Okay, and you should actually do this exercise and take it with the textbook expression. Great. Okay, so then whatever you get in the leading 3x3 part as the product of this rotation matrix and this rotation matrix, that will be sitting here as the rotation matrix, and in the final product whatever you get in the last column, that will be the translation, and that means this vector D will be this vector, this origin to this origin, this vector as expressed in this basis, and the final rotation matrix that you get here, that will have first column, second column, third column as uh, as these three unit vectors as expressed in this basis. That will be sitting in the place of R there. So now after having done this much, then you can immediately imagine that in this frame of reference I minus 1, if you can represent this frame I, then similarly in this frame I, you can represent I plus 1 and so on, and then you can say I can find out the transformation of link 1 with respect to link 0 expressed in link 0. Then in link 1, link 2, frame 2 has been expressed. In frame 2, frame 3 has been expressed. And then when you multiply all these, then the successive rigid body transformations together can represent the position and orientation, the 4x4 transformation matrix of the nth link, which is the last link, nth frame, as expressed in the base frame, relative to the base frame as expressed in the base frame. So that is end effector and robotic hand position and orientation. In a way, you have expressed that in terms of joint variables. Why? Because in each of these matrices, three of the parameters are always constant. They are design parameters. Only one is left, which is the design variable, which is the joint variable. So you must have noticed that here all these things are design parameters except this theta or this d, whichever is the joint variable. Only one variable is there. So now if you notice that, then you find that in this matrix only one quantity is there which is variable, which is a joint variable. In this another one, in this another one. So finally you have got n joint variables in terms of which you have expressed this transformation matrix, which is basically giving you the orientation and position of the end effector frame in terms of theta 1, theta 2, theta 3, theta 4, etc. So you can say that you have actually done what is called the direct position kinematics in robotics terminology. That is the finding out of the position and orientation of the hand in terms of the joint variables. So given thetas, you can always calculate this from this. Okay. So this is one symbolic way of writing it, in which this x, this theta vector is obvious. That is the vector, not in the geometric sense, in the linear algebra sense, of theta 1, theta 2, theta 3, etc. All the joint variables. In which a particular theta in this vector will actually be locally replaced by the corresponding d if that joint is prismatic. Okay. So and this capital X has to be another vector in linear algebra sense, not in vector in the geometric sense, which has the position variables and orientation variables of the pose of the end effector frame. That means position variables are obvious, x, y, z. Orientation variables may be phi, theta, psi if you are using Euler angles or roll-pitch angles, or k and theta with a constraint among them, or whatever it is. So depending upon your rotation representation in that problem, the variable listing will be here. Okay. Now, the point to note is that this is a straightforward mapping, in the sense that the way you define mapping or function in mathematics, that holds completely. That is, for every values of theta, every set of values of theta 1, theta 2, theta 3, theta 4, etc. This you can uniquely find out. There is given something, you get a unique X. Of course, the non-uniqueness may appear if you are using a particular rotation representation. So the matrix representation will be the same. Okay. So in a sense, it is a function, and you can evaluate it. Okay. And that is what we have done just above. So this is why you say direct position kinematics has no issues. It always exists and it is well defined. However, inverse position kinematics will have problems. We'll come to that soon. But before we come to that, let us see an example. And that example is important because even in planar case, many students, many people try to do all these paraphernalia of 4x4 homogeneous transformation matrices and so on. So, in planar case, all the rotation axes are along the z direction. So, a lot of matrices are unnecessarily handled, so that can be handled easily through plane geometry. So, that is why, as an example of this direct kinematics and inverse kinematics, I actually use a planar example, so that this thing settles in your head that for a planar problem you don't need any of these matrices. You can do a very simple, straightforward analysis based on your native knowledge of plane geometry, and that will be perfectly all right. Let us see one example. And at this point, I will take a little break, which will be for you actually extremely little, because I will stop recording and come back and continue. So this is a 3R planar manipulator. With the frame, you have the first link attached here of L1 length, second link of L2 length, L2, and the third link of L3 length. Okay, these are the 3 link lengths. And when I say link length, they make the same sense as in the ordinary sense of mechanism theory, in plane mechanism. These are the link lengths. And in the balance of the robotics rigid body transformations, if you had written the homogeneous transformation for these, it should actually come in the place of A1, A1, yes, A1. This would come in the place of A2. This would come in the place of A3. Okay. So now the direct position kinematics problem says that these L1, L2, L3, these are already known, and of course the twist angles, etc., are all 0 because it is planar. So all the revolute pairs are perpendicular, and this particular manipulator has no prismatic pair. If it had a prismatic pair in which the motion would be in the plane, then there it would be 90 degree. Now, here the direct position kinematics problem is that theta1 joint variables from the reference x-axis is theta1, and then this, if you extend the first link, if you extend, then from that extension, whatever is the direction of the second link, there is theta2, and then this theta3. These theta1, theta2, theta3 values, which are the joint variables, that is how the motors are positioned at this configuration. Then to find out the position and orientation of the hand. Position means x and y coordinate of the reference point here, that is this x and this y, and orientation, that is direction of this last link, which is the hand. Okay, so if you extend that and cut the x-axis, then you get this angle phi. Since this has become dirty, so I have reproduced a phi here. So with theta1, theta2, theta3 known, to determine these three output coordinates, that is, where is the hand and how is it oriented, x, y, phi, that is the direct position kinematics problem. And that is very easy because you see, this is x, which is OL plus LM plus MN. And OL is the projection of the first link on the x-axis, LM is the projection of the second link, MN is the projection of the third link. So get all the three projections, cos, cosine. So OL is this L1 into cos theta 1, LM is this AB into cos. You see, now here the angle will be theta 2 plus theta 1, that is projection along the x-axis. So L2 times cos theta 1 plus theta 2, and for the last one is further inclined. So theta 1 plus theta 2 is this extension plus theta 3. And make note, theta 3 is taken as the angle from the extension of this, not from the horizontal, because then orientation of this will not depend on theta 3 only, it will depend on earlier also. Okay, so relative orientation. So here with this we have each relative orientation given by the local only, and for the total orientation you have to add up everything. Fine. So this is x. Similarly, y. Y will be the height of A from x-axis, that is AL, and height of E from this height, okay, plus the height of P from the height of B. These three parts would be the sine component of L1, the sine component of L2, and the sine component of L3 with the appropriate angles. That would be L1 sine theta 1 plus L2 sine theta 1 plus theta 2, taking the proper orientation, proper angle, and plus L3 times sine theta 1 plus theta 2 plus theta 3. So why you get? What is the angle phi? You just see theta 1, you are in this direction. Turn further, theta 2, you are along this direction. Turn further, theta 3, you have got to the correct direction, phi. So that means the output orientation is theta 1 plus theta 2 plus theta 3. And you have got it. So that means direct position kinematics is just this. Express in terms of theta 1, theta 2, theta 3, these output coordinates x, y, phi, and you are done. Now, what would be the inverse position kinematics? Which would be very important practically, because practically you would say that my robot needs to go here to pick up this tool. Now, in order to go here for the hand, what inputs I have to give at the joints that is needed for the control. So here, that is for the inverse position kinematics problem, you would know where the hand has to go. Hand has to go at X and Y with phi orientation. So these things will be known. These three things will be known, and for that you would be required to find out the input variables, how to actuate your motors. Theta 1, theta 2, theta 3. Oh, it should be theta 3. So basically, you would need to solve these three equations for theta 1, theta 2, and theta 3. And that means that here x, y, phi, this side will be given. L1, L2, L3 are anyway design parameters. They are known already for a particular manipulator. You would have to find out the particular theta 1, theta 2, theta 3 joint variables required for that configuration in which the hand will reach the desired position and orientation. So you have to solve these three things with respect to theta 1, theta 2, theta 3. And now you see the solution is troublesome in the sense that the way you could give any theta 1, theta 2, theta 3 values and you would get some x, y, phi clear cut without any ambiguity. That is not so now, because now these are nonlinear equations. Robot kinematics will always give you nonlinear equations and you have to solve them. You do not have to evaluate a function. The value of the function is known and you have to find out the value of the variable. This is the inverse which is difficult. Okay. So these things are known. You have to find out theta 1, theta 2, theta 3. Solution of equations. Nonlinear, coupled, fine. So what you need to do? While solving equations, you try to eliminate. And one elimination is very clearly visible. Is theta 1, theta 2 plus theta 3, theta 1 plus theta 2 plus theta 3, that is actually known, phi. So use that phi value here and here. And from the first two equations, theta 3 goes out of picture. So do that. As you do that, you get L1 cos theta 1 plus L2 cos theta 1 plus theta 2. That is this. And the third term is known because this angle is known, phi. So put L3 cos phi and take it on the other side. X minus L3 cos phi. That is here. And this is phi. Okay, which you know. And this difference you call x bar or anything. Similarly, from the second equation, you get L1 sin theta 1 plus L2 sin theta 1 plus theta 2 is equal to y minus L3 sin phi. Okay. Call it something, say y bar. And now you find that theta 3 has gone out of business. Now only two unknowns are left, theta 1 and theta 2. And the eliminant equations are now here, 4 and 5. If you spend enough time with it, you will be able to solve these two together by eliminating another unknown. And one straightforward way to do it is to exploit the way the unknowns are appearing: cos, cos, sin, sin. And you know cos square plus sin square of any angle is 1. That means it does not depend on the angle. So what do? You square both sides of this equation. You square both sides of this equation and add them. As you do that, square and add is a standard technique in such robot kinematics or mechanism kinematics in general. You get L1 square cos square theta 1 plus from here, L1 square sin square theta 1 from here. So together L1 square. Similarly, L2 square cos square, whatever angle, plus L2 square sin square, that angle. So that is going to give you L2 square. Then to be term twice L1 L2 cos theta 1 into cos this plus twice L1 L2 from here, second equation, into sin theta 1 into sin this angle. So twice L1 L2 is common, and you see cos A cos B minus sin A sin B plus cos A cos B plus sin A sin B. That is cos A minus B. And here you have theta 1 plus theta 2 minus theta 1. That means just theta 2 remains. And theta 1 has gone completely out. On this square you have on this side you have two numbers. Just add, square and add them. And then take these numbers on this side, subtract, divide by twice L1 minus L1 L2. You get cos theta 2 and theta 2. That is very straightforward. Now I said find theta 2. But suppose this thing turns out to be larger than 1 or smaller than minus 1. Then what theta 2 you will find? And that means for this particular xy5 solution does not exist. Which is quite possible. For nonlinear equations, solution sometimes does not exist. What can you do? If solution exists, most of the time you would get two solutions. Because if theta 2 equal to 19 degree is a solution, then theta 2 equal to minus 19 degree also will be a solution. Because you have got the value of cos theta 2. Okay. So for example, if cos theta 2 is half, then you can say theta 2 can be 60 degree or minus 60 degree. Both will be valid. Can you see how they would look? This theta 2 is something like 19 degree or 18 degree, something like that. For the same position of B, A could have been up, okay? In which case it would look like this and this. And in that case, theta 2 would be clockwise, negative. So that would be minus 18, minus 19. So this configuration, which has been shown in this sketch, is called the elbow down configuration, and that other configuration is called elbow up configuration. Both are valid. In both the configurations, we can reach here, and therefore this can go wherever it is. Okay. So now you have got theta 2. Actually, you have got two values. Typically, two values. In a completely straight position, it will be only one value. Okay. Completely elongated or completely folded. In the case of 0 or pi, it would be the same value. Only one value in both cases. For every other valid value, it will be two possibilities. Now, if you use one value of theta 2, correspondingly, you will get one value of theta 1, which will be valid. And if you use the other value of theta 2, then you will get another value of theta 1. So, take one of the values of theta 2 and put it in one of the equations. If you put it in one of the equations, through some sign cos substitutions, okay, you would simplify it as cos theta 1 plus some angle equal to something. From that, you can get this argument angle theta 1 plus something, and this something is a number now. So theta 1 you get. Now again it is a cos. So based on that, you would get two values. Now these two values of theta 1 will not be just plus minus, because theta 1 plus this angle will appear as plus minus something. So that when you get rid of that angle, then theta 1 will be quite different. Okay, two theta 1 values. Now out of these two theta 1 values that you get for a single one of the correct theta 2 values, out of these two values of theta 1, one will be valid and the other will be invalid. How to detect the invalid one? You can put the same theta 1 values, both theta 1 values, in the other equation, which you are not using currently. Now the valid one will be validated by satisfying this equation. The invalid one will not satisfy this equation. This is the straightforward way to do it. Now if in the beginning itself, if you had used the theta 2 value not in equation 4, not in the cosine equation, but in equation 5, the sine equation, then also you would get two values, because sine of something, sine of an angle given will mean that that angle can be something or I minus something. So both values would be fine. Now one of these would be valid and other is invalid. In that case again, which is valid, you could validate it by putting it in the cosine equation. So cosine equation will give two possible values of theta 1 for every theta 2 from here. Sine equation also will give two possible values of theta 1. One of these two, one of this pair and one of this pair will be correct and common. And the incorrect one here and the incorrect one there would be different. So you can determine it from one of the equations, taking the other. Okay. Now that means for every value of theta 2 that you have got from here, you will get only one validated correct theta 1 value. So only one pair, theta 1, theta 2. And for the other value of theta 2, you will get another theta 1. So there will be two pairs. For each of these pairs, knowing theta 1, theta 2 values, you can then put that here at the top, equation 3, which you originally used to eliminate theta 3. Now known theta 1 and theta 2 values you can put there and get theta 3 trivially. Okay, this is the inverse position kinematics problem. This is how you solve for planar cases, which is very straightforward. Okay. And the issues you have seen, given an XY phi configuration, end effector position and orientation, you may or may not have solutions. When you have solutions, then you may have more than one solutions. Typically, you would have more than one solution. Only in totally extended position, the solution will be unique, and that also would be merged solution. That means a little change in data here and there would produce the two solutions, or make both of them complex. Complex means for realistic situation, it's no solution. So basically, that is what it happens. If you forcibly change the sinusoidal expressions to polynomials, then you would get complex solutions. You know how to make those complex solutions. Okay. So, in our sense of solution of kinematic problems, that would not make any sense. Okay. So, from the completely extended or completely folded configuration, if you change the initial data a little, x, y, phi, then either those solutions would vanish into complex domain, or those solutions will separate out and you would get two solutions. Fine. So here we stop for this lecture, and in the next lecture we will consider the issues for the general spatial manipulators inverse kinematics problem.